Okay, so welcome everybody. So it's my pleasure to start now for the first seminar in 2024 with for the GDR Industrial Partners, GDR Imabio. And today we welcome Abbelight. And so the session will be moderated by Lydia Danglo, who is an INSERM researcher and the scientific head of the neuroimage imaging facility. And she's also a member of the steering committee of the GDR Imabio. So please, Lydia.
Okay, so it's very nice to see you, all of you, because we are lots of people today. So we will begin with a seminar from Hervé Gauthier. So Hervé Gauthier is a product manager in Abbelight company. And then we will have a talk from Cyril Favard. So just to give you a small CV of Cyril. So Cyril holds a PhD in molecular biophysics, focused on fluorescence microscopy. After working 1 year for Hitachi, he joined CNRS as the research engineer and worked on biological lipids membrane using different type of fluorescence microscopies. He then spent 6 years at Fresnel Institute in the Mosaic team before starting a team with Delphine Muriot, who is a virologist. They both led this team in Montpellier. And actually, the team is studying the processes of the various assembly at the lipid membrane at the single or few molecules level with living cells. And to do so, they are using state-of-the-art fluorescence with micro and nanoscopy coupled to dynamic methods such as FCS and SPT-PALM. So I think that we have enough people. We will start with Hervé. So thank you, Hervé, to be here and to present Abbelight. Thank you.
Okay, great. I'm going to share now. So first, I would like to thank the GDR for the opportunity for us to lead this industrial presentation, and also especially Cyril for the next step after me. We are going to talk today about TIRF technology, and as you may know, Abbelight, we are known for application in super resolution, and we would like to extend a little bit the possibilities of application, because single molecule have led us to develop really cutting-edge technologies in TIRF elimination, and I will briefly present you this today, and then after I will lead to Cyril. Of course, TIRF application in SMLM, but also in live cell imaging, can be applied in a lot of different application and field of exploration in biology, and we have proven that we were able to develop a lot of different application and imaging technologies in these fields of biology. But the core technology of our system is based on TIRF illumination. So just briefly to explain how we can illuminate a sample. Of course, you certainly all know that the most easiest one is the epi illumination, which is a parallel beam upon the optical axis. And the advantage of this technology is that it excites the whole volume of a sample. But in the other hand, the signal-to-noise ratio is low. That's why there are some techniques to inclinate the beam and allow to illuminate the sample in another way. And for example, if you move in the optical axis the illumination source, then you will first have a kind of inclinated beam, and this is called eye-low. inclinated illumination. And what you can see, especially on this small thumbnail, is that you still have the possibility to excite a certain thickness of sample, for example, around 500 nanometers, but you improve dramatically the signal-to-noise ratio. And this is really important because in single molecule, signal-to-noise ratio is the key to have a good data acquisition and reconstruction. But then if we continue and also if we use the good lenses with high numerical aperture, we can still continue to move the beam toward the optical axis, and then we end up with a total internal reflection of the beam. And this is the TIRF illumination that creates an evanescent wave. And this evanescent wave have the characteristic to be really, really thin. I mean that you will excite 100 nanometers of above the cover slip of your sample. So it's really dedicated to certain kind of samples, illumination, but it's, for example, perfect for membrane imaging. And on the image, you can see that you really get rid of all the signal-to-noise ratio, but also the out of focus parts that you want to avoid. So TIRF is actually one of the easiest way to do optical sectioning. So basically, we are developing systems that allow us to move toward all of this illumination method and allow to choose the best one if I'm working on a really thin sample, or if I want to go a little bit deeper in my sample. And here you can see on the same sample what you will be able to get in terms of outcome. So the TIRF, Abbelight TIRF system, of course, with also can be capable of going to single molecule, is a system with adaptable to any inverted microscopes. It's based on the camera port, and the excitation and detection is on the same system. And what we can offer is the largest field of view of illumination of the market in this specific technology. And we worked very strongly to give you the most homogeneous and uniform field of illumination, because in TIRF illumination, this is one of the main pain points, is that usually you got central and small area of homogeneous illumination. So this is the first step that have been done now since the beginning, and this is really the core technology of our Abbelight system. The second thing is that we work now to offer live cell imaging to our customer. So not only in single molecule, but really in live cell imaging. And we worked on offering an automatic and reproducible TIRF adjustment. And I will show you that in the next slides. Also, we were able to design a system that now offers to do up to 4 simultaneous color in TIRF. And I will explain you. So first, the large field of view and uniform TIRF is because we own a proprietary technology called Aster, and this Aster technology is a way to scan the beam of the laser before injecting it into the lens, and it leads into what you can see on the right of the slide, that we can excite a much larger field of view. So, long story short, usual TIRF system, it's around 50 with a 100x lens, 50 to 80 micron by 80 micron area. Here we can go easily to 150 micron, which is 4 times more. So we can offer a 4 times bigger field of illumination, which is homogeneous. It does mean that you can image 4 times more data with one image. Also, the difficulty when you design systems that are really versatile is that you have to adapt optically to all kinds of devices. For example, we are able to install a system on an already existing microscope in a lab, but all the microscope systems are not equivalent in terms of optics. So we have to adjust finally the optics of our device to fit correctly and perfectly in the optimum illumination model. So that's why we are working on that, and we are really adapting our devices to the microscope, which is and the lenses which are utilized. So the topic and the target is and to and most obvious illumination. And how we can achieve that easily, because it also can be also a challenge in TIRF illumination. We have designed a protocol and a system to automatically calculate the perfect angles for the different illumination method, as epifluorescence, which is quite easy because you center the laser in the optics, so it's the most easiest to have. But for the ILO and for the TIRF illumination, we have a specific sample and algorithm that help us to calculate automatically the perfect position in the backfocal plane of the lens. We are also using some technologies that help us to really finely adjust the laser beam in the backfocal plane of the lens that leads to the best illumination. So this is really the target, to give you the easy way and automatic way to calculate the best angle. So it's not your eyes, but you have really data that help you to set these angles, and also help you to keep, I would say, to keep the best performances of your system all along its life. And so that's all for me. I would like to thank you for your attention, and I will lead now the talk to Cyril, that will also continue into this TIRF technology. Thank you very much.
Thank you. Virginie, I don't know, there's already a question for Hervé, so is he answering right now, or which is going on, and then we will answer at the end of the...
So the best maybe is to have the questions at the end.
Okay.
Okay, thank you.
So I'm just sharing my screen. One moment. Sorry. There we go. And is it okay, or do you see still these squares appearing on my screen?
Now it's okay.
That's good now.
Okay.
Now
Thank you. So thanks to Abbelight for giving us the opportunity to present what we've been doing for the last 2 or 3 years with collaborators in Institut Fresnel, working about one way to enhance the total internal reflection fluorescence microscopy using resonant dielectric multi-layers. So the work I'm going to show today is mostly the work of Anita Mutu during his PhD, and I want to mention that this is a real teamwork. If I can change my slide. So on the left, we have the team here in Montpellier, more applying the developments, and of course participating and calculating also some stuff, where Anita did a PhD here. And on the right, we have the SEMO group in Institut Fresnel. The SEMO group is more specialized on surface treatment and field enhancement using dielectrics and many other applications. And of course, I need to thank all the granting agencies that granted this work. So why, and this is, as I said, mostly the work of Anita Motu, sorry. So why did we do that? Because in fact, the TIRF microscopy has been renewed. So I guess most of you know that the TIRF microscopy is a very old technique. It just started to be launched in the 1970s. And it's been recently renewed with the appearance of the single molecule technology. So TIRF microscopy is an ideal tool to study individual particle imaging, particle binding to membranes, cell membranes, exoendocytosis, every kind of process that take place at the membrane of the cells, at the plasma membrane of the cells. And here in the team, we are mostly interested in the assembly at the single molecule level of viruses that are approximately 100 nanometers. So this TIRF has been coupled with different type of other optical tricks to get 3D super resolution imaging. So for example, TIRF has been coupled to SIM, structure illumination microscopy. As Hervé told you previously, TIRF has a big advantage because it is improving powerfully the axial resolution to get down to something around 100 nanometer. But of course, the drawback of this is that you don't have any improvement in the lateral resolution when you perform classical TIRF microscopy, and you're still limited by the diffraction. But if you couple that to structural illumination microscopy, then you can end up in an axial and lateral resolution around 100 nanometer. And if you go now to single molecule localization microscopy, you can get down to lateral resolution of approximately 40 nanometers while preserving this axial resolution of 100 nanometers. So here, just to illustrate you, this is one cell that has been transfected by HIV GAG protein. So on the left, this is the epifluorescence image of the same cell. Then you have the TIRF image of the cell. And then you have the TIRF coupled to palm microscopy image. And you can see on the palm microscopy image that you can start to see individual HIV viruses. So,
Cyril, may I interrupt you?
Sure.
Each time somebody is entry, you have the panel that is covering your title. So maybe you could move it to the.
Okay.
Maybe on the
If I do it like this, maybe
on the lower part, yes.
Yeah, I don't know. Honestly, I don't remember exactly the structures of my slides, but okay, I'll go like this. We'll see. Okay, so what I've been showing you is that finally a lot of development has been done, and you could question why start trying to do something even better, because it works quite nicely up to the moment. Although Hervé shown you before that you can have many different problems, including interferences occurring at the surface, so the image is not perfect, it's not flat, the illumination is not good, and so on. There is another thing that is often not taken into account in the theory, is that the TIRF microscopy is designed, well, it's considered for parallel beam illumination and a front wave which is perfectly flat. And in that case, what's going on is that if you look at the enhancement of the field at the surface of the substrate, then you start from 1. This is normalized at the angle 0. Okay, so this is the normal illumination towards the surface. And if you do that, then you can calculate what will happen about the enhancement of the electric field, which is in fact the illumination. Then you see that you go through a maximum, which is 3.5 times what is the field at the 0 angle. And this maximum occurs at the critical angle, which is the TIRF angle. And after this maximum, then again, the evanescent wave power starts to decrease, and it decreases quite linearly, but in fact, it's more exponentially. And the thing is that if you are able to stay at the critical angle, then you have the maximum excitation intensity, and you will have the best signal-to-noise ratio. But in real life, because you're using high numerical aperture objective, in fact, you are not illuminating with a parallel beam. You're illuminating with a beam that has a given divergence. And because of this divergence, in fact, the angle you span is not only the critical angle, but these are angles before the critical angles and after the critical angle, sorry, if you decide to illuminate at the critical angle. And because of this, you will have some propagative waves that will go inside your sample. And with these propagative waves, you start to have a weaker contrast. So one way to avoid that is to go to higher angles that are higher than the critical angle, the TIRF angle. But if you do that, then again, you have a decrease in the excitation intensity. So you will have a weaker signal than the one expected at the real TIRF angle. So what we decide to do is to try to find a way to re-increase the excitation power at an angle which is much higher than the critical angle to get rid of these divergency problem. So for that, you can use two different approaches. One approach that has been developed for a long time also is to use metal layers and to enhance the evanescent width by using surface placements. You can see here, for example, in that paper, that you can improve the evanescent wave up to 85 times as compared to what you will have on glass surface only. And another approach is using block surface waves, it's called, and these are dielectric multilayers. So it's an alternance between high refractive index layer of metal-like metalloid system and low refractive index. So this is the real principle of a dielectric. And if you use that you can even think to get up to 10 to the power 4 enhancement at the surface. Of course, these enhancements, again, are just calculated for totally parallel illumination of the system. So if you look at the pro and cons of the system, if you use metal, the field enhancements, it's much lower than the dielectric multi-layers. But if you look at the tolerance to the divergence of the faisceau, then of the beam, sorry, then the metal will be much better than what we have on dielectric multi-layers. On the other end, the multi-wavelength capacity, which is in fact to enhance at different wavelengths, is more in favor of dielectric multi-layers. And finally, what was more interesting, knowing that we want to do that with cells and possibly organisms organized later on, then the biocompatibility is a very important parameter. And with metals, usually it's quite bad, whereas with dielectric multi-layers, it will be good because the last layer that we will deposit on the surface is glass, as on a cover slip, as on a classical cover slip. So what is the principle of this? In fact, you just take a cover slip and then you add some layers of high index and low index that you alternate to, and you end up with the last layer, which is similar to the glass. And with this, in fact, you can make a new, I just moved this, sorry, if I can. You can make a new cover slip, as you see here. So this is an example of a prototype that we made. Here you have the glass cover slip, which is 170 micrometer thick. And we just add some coating on the surface, the dielectric multilayers coating, which is 1 to 2 micrometer thick. So if you compare to this 170, it doesn't change a big it doesn't change drastically the thickness of the cover slip, so it does not introduce any interference into the optical system. So of course, then afterwards you need to define what are the illumination conditions, at which angle you want these enhancement to appear, this resonance to appear. You need to know what are the different dielectric material, refractive index, and so on. Once you got all these parameters, you can start to design this in order to get an enhancement. Before, I just wanted to show you that if we look at the cell growth on the surface of glass on the left side, on the surface of the dielectric multilayers on the right side, we don't see any difference. So the cells are growing exactly the same way. Either they are growing on the dielectric multilayer or on the normal glass surface. So if we have all these good parameters, then we can design a system that will have a resonance here we decided to choose 68 degrees, which is far enough from the critical angle and not too far from the limit angle you can access with high numerical aperture objectives. But still, you can design something that will have a resonance which is 150 times higher than the value at the 0 incident angle. So this is in case of a perfect parallel excitation beam, which is, I told you, not the truth in the real life. We also define here a parameter eta, which is the enhancement as compared to what it will be if we stay on the glass surface. So if you compare to what it will be on the glass surface, of course, we don't have 150 times anymore, but we have 150 times divided by 2 point something, which end up in a 65 time enhancement. So as I told you, this is what should happen if we are on a planar wave condition. But in a high numerical aperture objective, we are not on planar wave condition. So we needed to implement some calculation in our system to take into account what is the divergence of the beam in our microscope. And if we do that, which simply by using this kind of analytical approach where we integrate the difference of the field as a function of the divergence here, then we see that, so no, I need to move it the other way around, sorry. Then we see that the divergence is changing that way. So here is the maximum where the divergence, here is the maximum of the enhancement, which is close to 65 times, where the divergence is close to 0, okay? But if you increase the divergence, then you rapidly see that the field is strongly decreased, but nevertheless, you can still end up in something which is around 20 times in terms of enhancement. So here is the same. This is only a slice of this plane you've seen here. And for example, here is the angular divergence range that you can, that you can have usually in TIRF microscope. So it goes from 10 millirads to 20 millirads. And with this kind of prototype, we still can achieve something around 10 times increase in the enhancement of the field. However, we have to take account another parameter, which is that we are not looking at the exaltation, at the enhancement of the field at the surface, but we are looking at the fluorescence that is collected through the same dielectric multilayers from our sample. And if we do that, we need to consider now an enhancement of fluorescence and not only an enhancement of the excitation field. And the enhancement of this fluorescence is, in fact, only the enhancement of the excitation fields times the average transmission of our dielectric multilayers. So if we consider, for example, any photons emitted from the sample and going through the dielectric multilayers, we can establish a map of what will be as a function of the emission wavelength and a function of the angle of the fluorescence photons emitted from the sample. We can establish what will be the transmission efficiency, which is from 0 to 1. Okay, and on average, we have a transmission efficiency which is something around 60%. So if we couple all this, now we end up in an enhancement of fluorescence, which is only 4 times as compared to the glass. Nevertheless, it's still 4 times. And now we have to question, is it something that we are really also observing? These are whole calculation. And now we need to perform the experiment. So here on the left, for example, these are fluorescent beads excited at 561 nanometer. And we scan the angle of excitation on the glass cover slip, and we record the fluorescence image. So on the left, this is on the glass cover slip. So we see from 0, we increase, we will go through the TIRF angle here, then we start to decrease again. So if you look at the same movie and look at my arrow on the graph, you see that you go there, you increase, up, you go to the TIRF, and then you start to decrease again and decrease again and decrease again, until you have no signal anymore, okay? Now on the right, this is exactly the same experiment, but performed on our dielectric multilayers. So again, you increase, you go through you go through the TIRF angle here, and then you decrease and you re-increase again, and you go through the exaltation, the enhancement of fluorescence. So maybe I'll show it from here. Here we are at the TIRF angle. Sorry, I go back to 62. So we will go through the TIRF angle. Here we are. Then we start to decrease again, and then we re-increase to go through all the exaltation of fluorescence here. So we have now an experiment that works perfectly accordingly what theory predicts, and we can quantify what is the enhancement of fluorescence. If I can go to the next one, sorry. And if we do that, what we see is that theory predicts a 4 times enhancement, and here in this system, in this experiment, we measure a 3 time enhancement. But as you can see here, we don't have a very nice Abbelight TIRF microscope for the moment, and we have indeed a divergence of the beam, which is much larger than what the calculation that what we put into the calculation. And this is the reason why we see a decrease in this enhancement of fluorescence. So I will get to something more about the design. In fact, if you want to enhance correctly, you can enhance infinitely, depending on the absorption of the last layer. And this absorption, in fact, is given by the imaginary index of the system. It's a little bit technical, but I want to explain you how we did that. If you consider that you have the silicium, the oxide of silicium, which is, let's say, something like glass, okay, then this imaginary index is considered to be around 10 to the -5. And when you design the system and optimize like this, in fact, unfortunately, what you see is that if you start to make errors in the real value of these optical parameters, then you drastically decrease the real value of the enhancement of fluo. And this really becomes a very strong problem when you go up in divergence that are close to what you observe in objective-based TIRF microscopy. So we need to redesign everything in order to decrease this discrepancy at high angle of divergence. And for that, we made different calculation and we fabricated different type of things. And we ended up in seeing that if you have a lower absorption coefficient, in fact, you will have something that will not change that much as a function of the absorption coefficient. So even if you make an error at the fabrication of the system, it will not weight so lot to what the calculation predict in terms of enhancement. And we control all these, and we even show here the curve as a function of the error on the top layer. So for example, here you have the imaginary index of silicium with a given oxidation state, then the same silicium with a higher oxidation state, then the silicium with a fully oxidated system. So we fabricated this first prototype that we put under ozone for 10 hours to increase the level of oxidization, and we end up in fabricating this dioxide of silicium last layer system. And regarding our calculation, we predict that the enhancement of fluorescence will increase from 3 to 5, and this is perfectly controlled. And in fact, this is what the calculation predicts, and this is what we observe on sample on beads deposited on the surface of our system as compared to what we have guessed. So now we can control not only the divergency, but we can also control what will be the enhancement by knowing exactly what has to be the state of our last layer. So this is the end of the technical part. Just to tell you what we can do with this, of course, because this is a highly tuned system, we also need to take into account how this resonance will change as a function of the refractive index of the sample, which is most of the time not really known. So if we go from 1.33, which is water, up to 1.5, which is considered to be higher than cells, then we see that the resonance efficiency is almost always the same. What only changes is the angle where the resonance occurs. But again, this is calculated, this resonance here, and the width of the resonance is calculated for parallel system. And due to our divergence of the beam, in fact, when you observe that under the microscope, you will not be able to see this difference in the terms of angle. It will just appear at the same angle. On the other end here, if the resonance is highly fluctuating with the excitation wavelengths you're using. So it gives you the opportunity to do multicolor imaging because the resonance occurs at any kind of wavelength. But the truth is that the intensity of the resonance as well as the angle of the resonance is not the same. So you have to adjust the system as a function of this. This is something we're currently working on to end up in perfectly linear and totally equivalent intensity system in order to avoid multicolor imaging, in order to avoid aberration into this multicolor imaging. So I will just end up with some example of this. So here, these are HIV-1 gag viral particles that we observe using this enhanced objective-based TIRF microscopy. So we excite at 488 nanometer, although the system was optimized at 561. It's still working quite correctly, okay? Here is what predicts the calculation. On the left, this is what you observe on the glass cover slip at 70 degrees, sorry. And on the right, this is what you observe on the dielectric multilayers at the same angle. And clearly you see that you start to see appearing. Of course, we deposit the same sample on a cover slip, which is splitted in two. On one side, there is the dielectric multilayers. On the other side, this is pure cover glass. And we just compare the two images. And this is what you get. You can do the same with source curve. Source curve is much more difficult to produce, so usually you don't have the same concentration than HIV gag, but still, if you go to this dielectric multilayer, you start to see appearing multiple particles that you don't really observe on glass cover slips. Although, as I told you previously, the concentration is the same on the left and the right image. Finally, you can also do that, if I can move this. Or maybe I can hide. Nobody's going to enter now. No, that's not a good one. Okay. So you can also do exactly the same kind of experiment on a cell that is transfected with this HIV-1 gag GFP protein. So here we perform the experiment on the glass. We image at the epifluorescence angle. Okay, then we do the same at the TIRF angle. So you can see, as it was previously mentioned by Hervé, that there is a clear benefit in the signal-to-noise ratio. And then we go up to the resonance of our system. Of course, as predicted by the calculation, you start to see a decreasing in the signal-to-noise ratio due to the loss of signal. And if we perform exactly the same experiment on the dielectric multilayers, then you go again through maximum by TIRF, but this maximum gets even much better when you get to the resonance angle. And you can try to look at that in terms of signal-to-noise ratio just by for example, looking at the profile around one line. And if you look at the profile here, this is the profile in the epifluorescence. So the profile tells you that you have a big envelope in the epifluorescence and you have very, very low details of the signal here, okay? If you go to the TIRF, you have the envelope plus some details on top of it. And if you go to the resonance, then you start to lose the envelope, which is confirming the fact that because of the divergence, you have propagative. So if you go to an angle which is much higher, you lose this propagative, so you're really TIRF. But then, of course, then you don't see a big increase of in the signal to noise because you are losing signal. On the opposite, if you do exactly the same on our system, then what you see is that if you go up to the resonance, not only you don't waste signal, but you even gain in terms of signal. If you look at peak to valley ratio, you even gain in terms of signal to noise value as compared to the classical TIRF microscopy. So this is what I've shown you previously to show you that we can even do multicolor enhanced imaging. These are, for example, the different resonance on beads on the same glass surface with the different wavelength, 405, 488, 561, and 640. And just to end up this is to show you a very, 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 very preliminary results that we obtained performing palm microscopy on cells that are transfected with HRV1 GAG MES 3.2. So here, this is what you observe on glass on a classical TIRF surface. If you put 3 kilowatt per centimeter square of 561 nanometer, this is what you can reconstruct. So these are images. I think these are 4,000 images, okay, only. This was just to try if we see something. And we perform exactly the same experiment on the dielectric multi-layers, but now we decrease the laser down to 0.8 kilowatt per centimeter square. And finally, you can hardly make the difference. And just to give you an idea of the pointing precision, although we have low values of power here and even more here, we end up in a pointing precision, which is quite similar in the two cases. And to show you something that Hervé presented just before, this is the first try on the TIRF microscope. We just scanning the angle towards the end of the objective here, and we are recording the fluorescence on our dielectric multi-layers of beads that are emitting and that are excited at 561 nanometers. So what you can see here, you see perfectly what the calculation predict. Then you go to the TIRF first maximum, then you decrease again, and then you see the enhancement, which is quite narrow, showing you that here, for example, the divergency of the beam is nicely controlled, and then you decrease again. And I think that's all. In conclusion, what I just wanted to tell you is that we have develop some innovative, biocompatible, and versatile NN substrate that can be adapted to any commercial TIRF microscope. In objective-based TIRF microscope, the beam divergence is a big issue. So of course, the lower it is, the best it is. So this is really a function of your microscope, because it generates usually a 10-time loss in the enhancement. But nevertheless, we were able to correct and predict the experimental fluorescence enhancement. This is all for me. Thank you for attention, and I'm ready to take questions. And I'll stop my screen sharing so that I can see you, or at least the questions.
Okay, so let's start the question. I think we had a previous question from Arnaud Sergi for Hervé. Which was, you mentioned that you have a higher SNR. Is it in the order TIRF best than ELO and best than Whitefield?
Yes. Actually, the TIRF gives the higher signal to noise ratio, and then the ILO, and then the Whitefield, and this is
to ask question. The session is recorded and will be on YouTube afterwards. So if you don't want to appear on the web, just switch off your camera. So do we have any other question? You can raise your hand or ask it in the chat. Yes, so we have a question from Davide Normano. Who was asking, how robust is the dielectric multilayer with respect to the chemical treatment? For instance, silanization to produce a PEG-covered cover slip for in vitro experiment.
Okay, so we didn't try that, so I can't answer that this is very robust to silanization. However, if I understand exactly what silanization is, it's just an oxidization of the surface to couple this PEG to the surface. So you want to produce from SiO2 to SiO2. From SiO2 to SiO minus or something like that. So meaning that you will start with acidic procedure or strong oxidization procedure. So of course, if you leave it too long into your bath of oxidization of the silice, you will certainly end up in a problem. So I think the good answer is you must try, and you certainly need to adapt the protocol. However, it should behave exactly like glass surface behave. So the last layer is hundreds of nanometers. It's not 10 nanometers. So I've real difficulty to tell you how fast you generate these negatively charged SEO minus on the surface, but it should work.
Okay. So he says thank you. In between, for now, there is no raised hand, so maybe I will ask one. You mentioned about the divergency, and I wanted to know how big can be the divergency from one brand to another. Do you have an idea of that? And let's say that if you set up your slide for your laser, would it be adaptable on another mic, or should you adapt it depending on the laser?
So in fact, most of these microscopes have lasers that are fibered and coupled to the entrance of the system, and in general they have optics that are supposed to adapt the system so that you focus perfectly to the back focal plane of the objective, and then you should end up in being perfectly parallel at the outside of your objective. But of course, this is not true. And this is mostly depending on where you focus exactly on the back focal plane or not. So I guess that, to be honest, most of the brands are able to focus perfectly on the back focal plane, okay? So at the exact position of the back focal plane, but then after, it depends how robust the system is, because some will focus forever at the back focal plane. That's not true, but some will be de-aligned very rapidly, depending on what is the optics and blah, blah, blah. So if you don't realign your system every time, then you will start to have a kind of drift towards something which is not aligned at all. So in fact, these multi-layers are also one way to measure that, because depending on the width of the enhancement you see, you can have an idea of how divergent your beam is. So as I've shown you in the microscope we had here, the beam was quite divergent and it was not correct. And the alignment procedure is a pain in the ass. So because this is a commercial machine, I will not give the name of the brand, but you cannot enter into it and you cannot do what you want to do exactly. So it's a real pain. So of course, what we saw is that time after time, the divergence started to begin more and more. In the Abbelight system, this is the last line I've shown you. If you look at the resonance peak, it's very narrow, showing that the divergence is quite good. It is certainly less than 1 degree, okay? So when using these cover slips, even if you don't want to use them for doing your experiments on your cells, you can still have an idea of the divergence. And if you have an idea of the divergence, it will also tell you if you better place your laser at the TIRF angle, because the divergence is very narrow. So you're quite good when you're TIRF. You will have a good signal to noise ratio. Or if you better go even further in the angle, and then you will decrease the signal to noise ratio because of loss of signal, but you will not have this propagative wave into your system. So these cover slips could be used as system to calibrate your system.
Okay, good. We have a question from Charitra Sri Senthil Kumar, who is asking, do you know if the incident polarization of light is preserved or if it is distorted at the sample plane?
So no, we don't. What I can tell you is that clearly this dielectric system works for a given polarization. And if you tilt the polarization by 90 degrees, then the enhancement drops drastically. But I can't tell you what is the polarization state at the sample. Honestly, we didn't try to do that, and we did not even make any calculation on that.
Okay.
I saw another one also in the chat. You mentioned that the power used is lowered thanks to the dielectric cover slips. Can we say that the cell receives less power and that it reduces the phototoxicity? No, we can't say that, because in fact, it is supposed to receive more power. In fact, we decrease the power to do palm microscopy because the enhancement at the surface is in fact confining in some way the electric field here. So we need to push, it's like we are just wasting less electric field. So we just have to put less from the laser to even get more at the sample. This is what we're doing, in fact. So we don't have less power at the sample. We have more.
Okay.
Maybe if I can just ask a naive question, maybe I missed it, but Cyril, did you mention the thickness of these multi-layers? And is there any effect or problem with the objective that we have, which are corrected for a specific thickness of the cover slip?
So yeah, I did mention it, but
okay, sorry.
No, I'm kidding. But the thickness is 1 to 2 micrometer at most, and the thickness of the cover slip is 170 micrometer at most. So at most, let's say it's 1% more. So pure optician will tell me it does something, but I think it doesn't do anything because the correction of the objectives are not precise to 1%. Okay, so we're just changing the thickness by 1% of its original value, which is totally negligible. But if I want to be perfectly rigorous, we didn't check if there was a real effect in the depth of field, in the aberration, and blah, blah, blah. But for 1%, I mean, I think we will have a big issue to find any effect if it does exist.
Maybe I have another question. I was wondering, you mentioned at one point the divergency with different wavelengths. Do you think that you could, let's say, optimize your laser or your wavelength so that the divergence is close enough to have only one correction for all of them? Is it feasible?
So this is what we're working on. So in fact, we are currently working on designing these dielectric multi-layers to have a correction at the surface for 2 wavelengths for the moment, so that the depth of field will be the same for the 2 wavelengths and independently of the divergence and so on. So this is exactly what we're working on. And it's not so easy. This is the only answer I can give you.
I
it's
can
not so
imagine.
easy.
And it's a no more question for now. I have a question for both of you concerning the homogeneity of your TIRF system, because Hervé, you mentioned that you have a big field of view of 150 micron, which is really cool. For people doing neuron, it's really, really big field of view. And I was wondering, so you mentioned that it was supposed to be homogeneous, Hervé. How far is it true, I would say, depending on the wavelengths, and is it totally homogeneous for all wavelengths and everything?
Yes, actually, we have tested that for all the laser, the usual suspect wavelengths, from 405 to 640, and this is because we use a really proprietary technology to scan the beam of the laser into the backfocal plane. So let's say that it's not only, so there is the question of laser alignment and laser injection, as Cyril mentioned. It is something quite important, but also before the lens, we have some other devices that allow us to really let's say, expand the beam in a way that it's really homogeneous on the whole field of the 150 microns. It could be even more a little bit, but reasonably we say that we are sure for 150.
And so do you provide with your system both the laser and your system, or could we plug your system on a pre-existing laser somewhere?
So actually, the solution is a really an all-in-one. So we provide the laser bench, but some of our customer so we could use a laser combiner, but we cannot ensure the full quality of the beam to be injected into the microscope and in the optical system. It's possible, but today we are moving toward, let's say, a package solution that include our laser combiner, which is specific to this and where we are sure to control all the points.
Okay. And for you, Cyril, concerning homogeneity, I was wondering, you are working on epithelial cells infected, right? On your
Not only T cells, also, yeah. Here I use epithelial cells because they are spreading and it's very nice, but this is more for imaging than for research.
And I was wondering if you take, let's say, cells that are less flat, do you have distortion with your device, or is it still okay even for some cells that wouldn't be as homogeneous as flat epithelial cells?
No, so again, we try on T cells. It works. So they are less flat clearly than these other cells. And then I don't have any other experimental evidence, but I don't see any theoretical reason why it will change anything. So, except maybe if there is a drastic change in the refractive index value, but clearly it's not the case. So there shouldn't be any real issue. In fact, our device does not change the appearance of the electric field on the surface. So for example, if you have one microscope that is using only one position on the objective, you usually end up in having some interferences on your field of view when you perform TIRF. Our device will not change that. It doesn't make the system to become perfectly flat. It doesn't change these interferences. They're still occurring. So it's more that it really enhances the field here. It doesn't really change the spatial XY spatial properties of the field. It changed the Z properties of the field.
And maybe another very naive question. When you have an autofocus system with a 800 nanometer laser line, for example, would it be compatible with that?
Didn't try. And this I can't answer. So, but
okay.
It should be. We just need to redesign the cover slip for that purpose. There's no clear reason why it should be different. Then, of course, if you go to a 2-photon absorption or things like that, might be another problem. But if you're still in a single photon or whatever, there's no reason why it should change.
Okay.
To my understanding. My colleagues of physics said they were supposed to answer that kind of question, but I don't see them. So
maybe you will answer it if there is an episode 2.
Yes, exactly.
Exactly. Okay, do we have any question within the audience? Don't be shy. Speakers are there for you, so you can ask whatever you want. In science. I think we are done for today. Thank you very much, Hervé and Cyril, and thank you, Virginie, for organizing everything.
So thank you very much. So the Abbelight, Hervé, and Cyril, and also Lydia, So the next meeting will be the 5th of March with the Zeiss company, and it will be about they propose to talk about lattice light sheet. So
Okay,
see
super.
you.
See
Yeah.
you soon.
See you
Bye-bye.
soon. Bye. Thanks a lot, all of you.
Thanks a lot. Bye.